Continuing on with the LED, we'll just briefly go through how an LED works and why the blue LED was so revolutionary. And considering the length of this video, it will probably be split into two parts. One explaining how an LED works, and the second explaining how the blue LED came about. So as we know, an LED has two legs, an anode, a longer positive leg, and a cathode, a shorter negative leg. And in semiconductor physics, an anode represents a p-type semiconductor and a cathode represents an n-type semiconductor. And think of the p-type semiconductor as the one that has the less amount of electrons, which are called holes in the industry or in semiconductor physics. And the n-type semiconductor as the one that has the extra electrons. And the distance between our p-type semiconductor and our n-type semiconductor is called a p-n junction, and it's why our LED works the way that it does. And simply put, what happens is that electrons will flow from the n-type semiconductor to the p-type semiconductor. And at the junction, the electrons will combine with the empty space or the holes that we mentioned earlier. And that process is called recombination. And when this happens, the electrons will lose energy and release it as photons, which is essentially the light that we see being emitted by the LED. So now let's actually move forward into why the blue LED was such a revolutionary discovery. We know when the LED was invented, it wasn't such a big issue to produce red LEDs and green LEDs, but it was the blue LEDs that were particularly tricky to bring to life. And that's because the color that you see on an LED is the distance or difference in energy between two bands. One being the valence band, which is the band that has a lot of electrons stuck to it, and the other being the conduction band, the one where electrons are free to move about. And then the energy lost by electrons moving from the valence band to the conducting band, which is called the band gap, is what actually allows us to see the colors that we see. Therefore, a red LED would have a band gap of 1.8 to 2 electron volts, meaning that your semiconductor material has to actually be capable of delivering that band gap or allowing that difference of a band. Same thing for the green LED. The green LED has a band gap in between 2.2 and 2.4 electron volts. It was with the blue LED that was very tricky to sort of, get that band gap, because again, it had a very big band gap between 2.7 and 3.4 electron volts. And back then, the general material or the general consensus for the material that scientists used, that material wasn't capable of delivering that band gap to allow a blue LED to be. Same thing for green. For green, it is a bigger band gap, but still achievable to an extent, and that is 2.2 to 2.4 electron volts. And that material early LEDs used was gallium arsenide. And no matter how well scientists could optimize gallium arsenide, still, there was no way it would have a big enough band gap to actually accommodate a blue LED.